In this video, we'll be discussing post hoc analyses for ANOVA. Post hoc is simply a Latin phrase meaning after the fact. Thus, these analyses are conducted after the fact with ANOVA. After a statistically significant ANOVA, we utilize these analyses to determine where statistically significant differences lie between groups. I'll also mention real quick, just on the side, post hoc analyses are done for several other types of tests. Post hoc tests are often called that because they're conducted after the fact of a study. But post hoc analyses in ANOVA have a very specific interpretation. So post hoc is a broadly used term, but just like analysis of variance can be considered from a broad perspective, post hoc can be considered from a broad perspective, but in the context of ANOVA has a pretty specific meaning regarding the tests that we're going to discuss in this class. There are a variety of different post hoc analyses that can be implemented after our ANOVA, and I'm just going to list off a few of them. We're not going to talk about all these, but you have Fisher's LSD, you have Tukey's HSD, you have Bonferroni's correction, you have Sheffey's test, you have Duncan's test, you have Dunnett's test, you have a lot of them. And it might come up, why are there so many different types of analyses that we utilize for post hoc analyses in ANOVA? We just have to compare the groups, right? Well, it's a good question. So let's jump into that question. This is one of my favorite comics from a website called XKCD. Ultimately, we have a person running in saying jelly beans cause acne, and then our lead scientist saying we have to go investigate and making everybody quit playing Minecraft and saying we found no link between jelly beans and acne. That settles that. I hear it's only certain colors of jelly beans that cause it. Okay, well, here we go. And so we go and test, and we test all the different colors: purple, brown, pink, blue, teal, yellow, magenta, turquoise, red, salmon, gray, tan, cyan, green. Oh my goodness, green jelly beans link with acne. Mauve, beige, lilac, I can't pronounce some of these, black, peach, orange, all of these different jelly beans we test and find that amidst all of our tests, we have one that's statistically significant. And the news is there's only we ran 20 tests, one was significant, so 5% of the tests were significant, and that there's only a 5% chance of coincidence that green jelly beans are linked to acne. All right, so that's our context here for this particular snippet of that comic. The idea is that if we run many, many tests, just by chance, there's going to be some that are significant. Recall that our alpha of 0.05 was indicating that the null hypothesis could be right 5% of the time, and we would accidentally reject it. That's the error rate we were talking about, is accidental rejection. So if we run a bunch of tests, we increase the probability of those accidental rejections. Every test has the probability of an accidental rejection. So if we break it down and then we run all of these and all of these and all of these tests, each one has its own chance of accidental rejection. And so we want to be careful. We want to be really careful when we're conducting post hoc analyses, specifically analyses with many analyses associated with it. And there's going to be many analyses associated with these post hoc comparisons, because we want to make sure that we are not drastically increasing our error rate when we're doing these comparisons. Now, sometimes this idea is called the multiple comparisons problem. And it's a good description because it happens anytime we compare multiple different things using inferential statistics. It's important to realize that this isn't just a problem with post hoc tests in ANOVA. This is a problem anytime you implement many inferential statistics. So if you have lots of inferential statistics, the probability that one of them is wrong is increased. So for tests that don't really account for that, and there's a post hoc analysis procedure that doesn't, called Fisher's LSD, these simply have a higher error rate than what you specify. You specify alpha equals 0.05, thinking you have a 5% type 1 error rate, and unbeknownst to you, that error rate is higher. How much higher? We don't know. We don't know, but it's higher, sometimes drastically higher. So if we want to do something that accounts for this, my recommendation is to use Tukey's HSD. So in the ANOVA, what we're trying to do is we're trying to compare each group to each other to figure out which pairs are different from each other. Kind of as we saw on that graph, we had the three groups, the community service learning, the experiential learning, and the didactic. And we want to say, okay, well, which ones are actually different? So we wanted to say which pairs of groups are different from each other. Is community service different than didactic? Is experiential different than didactic? Is community service different than experiential? We were comparing pairs. We want to say which pairs are different. For that goal, the Tukey's HSD is really the best choice of your different comparison options. Now, if you don't have many groups, then Bonferroni is also a reasonable choice. And actually, I want to talk a little bit more about Bonferroni in detail, because while Tukey's HSD is really good for ANOVA, Bonferroni is a fantastic choice, not just for ANOVA, but for really any statistical case where you have multiple inferential statistics. Like we said, this isn't just a problem with ANOVA, the post hoc comparisons. This is, in the case we were describing, we had three comparisons. We had community service learning to experiential, that's one. Community service learning to didactic, that's two. Experiential to didactic, that's three comparisons. But if I ran three chi-squareds, this could be a problem with that. So it's not the fact that we're in post hoc ANOVA land that's creating this problem. It's the fact that we're implementing multiple comparisons, and the number of comparisons we implement goes up drastically as the number of groups increases. Now, again, Tukey's HSD, perfect for post hoc comparisons with pairs of groups in ANOVA. So Tukey's HSD is my default choice for post hoc in ANOVA. Bonferroni is a fantastic choice because it works in almost any situation for inferential statistics. So I really like Bonferroni. Not necessarily for ANOVA, it's a little bit too conservative in ANOVA, but I like it because I can use the principle of the Bonferroni correction in any statistical test. I can do it with a chi-squared, and we didn't talk about any of these procedures with chi-squared. I can do it with fancier ANOVAs than we're going to talk about. I can do it with other analyses that we'll talk about. If I were implementing one of those fancy ones, discriminant analysis or logistic regression or regular regression, I can do Bonferroni's correction with all of those analyses. And that's why it's really, really handy. And that's why we have a whole slide on it right here. So essentially what we're going to do in Bonferroni is we're going to figure out what do we want our error rate to be. So typically that's 0.05. And we say, okay, this is what we want the error rate to be for all of the tests done in the study. If the errors add up between each test, we want them to add to 0.05. Like that's how the chances we want of anything in this study to be an error, we want it to be that. So again, typically it's 0.05. But now we're going to call it not alpha, but we're going to call it the family-wise error rate, indicating that this is something that we want for the whole family of tests conducted in our analysis or statistical story. Now, what we're going to need is we're going to need that error rate, and we're going to need the total number of tests that we conduct. So let's say I'm going to run 10 tests, let's say I'm going to run 5 tests. That'll be perfect. I'm going to run 5 tests, and I've got my error rate for the whole study is 0.05. That's the total family-wise error rate I want. From here, what I'm going to do to implement the Bonferroni correction is I'm going to divide that family-wise error rate that I specified earlier, 0.05, by the total number of tests. So in my case, if I'm running 5 tests, I would take 0.05 and divide that by 5. That gives me a result of 0.01, And that 0.01 is what I'm going to use as the alpha for each individual test. So I've got 5 different tests. Normally, I was comparing each test to 0.05. But now, after implementing the Bonferroni correction, I take my family-wise error, divide by the number of tests, get 0.01. And now for each of the 5 tests, I'm going to compare to 0.01 or use alpha of 0.01 instead of 0.05. What that does is then when I add the errors from all 5 tests together, 0.01, 0.01, 0.01, 0.01, 0.01, my total error rate is now 0.05 or 5% for the whole study error rate. I'll say that the math is a little more complicated than that, but that is a useful intuition. Now, incidentally, it's that complicated math that make this not the perfect solution for everything. This is a pretty good approximation when the number of groups is relatively small, though it might be a little conservative, a little bit of a lower type 1 error rate. But as the number of groups increases, this becomes almost painfully conservative. So you want to be a little bit careful. If you're running 10, 15, 20 tests, this can be a bit painfully conservative in the sense that you might have to have massive differences to determine a statistically significant difference using a Bonferroni corrected adjustment or a Bonferroni corrected type 1 error rate. So it's something to consider. Again, this is a good default value. And if you're running massive amounts of tests, realize you're also increasing the chance of error relatively drastically. So be careful about that. Bonferroni, though, is a good default correction to be used. While it's not perfect with large numbers of groups, and especially with ANOVA, where if I add one more group, I add 4 more tests or 6 more tests. I guess it's a geometric pattern, right? So if I had one more group, I had 4 more tests. If I had another group on top of that, I had 5 more tests. If I had another group on top of that, I had 6 more tests. So that they keep increasing the number of tests you add. With that, it's important to keep this in mind because otherwise you're going to be flooded with a whole bunch of different tests and not be corrected. So Bonferroni's correction in ANOVA, because of how many tests we can run, it's better to use a more precise method like Tukey's HSD. Sometimes it seems like a good thing to be more conservative. Hey, I have less error, but consider that also means you're increasing the chance that you don't find something you should have. You're increasing your type 2 error when you lower your type 1 error this way. So it's not that you have less error, it's that you have less of one specific kind of error. You're making less accidental significant claims, but you might be making more accidental non-significant claims. So that's a conservative test in statistics, is one that makes less accidental significant claims, but potentially more accidental non-significant claims. And Bonferroni does lead to that second type of error, more accidental non-significant claims, as kind of an ancillary or a corollary result of being more conservative with the type 1 error rate. So be careful. Now, I'm saying all this careful stuff. On the other hand, Bonferroni is a fantastic tool. I love this because it can, again, be used with any inferential analysis. You can use this with things you've never even heard of yet. And it's something that should be implemented a lot more often than it usually is. Typically, if your p-value is on the borderline and you've run multiple statistical tests, Bonferroni correction is going to suggest that p-value is not statistically significant. And this can be a good way to quantify that if you are looking at multiple tests. Hey, just how low should that threshold be? This can give you a good round number to maintain that family-wise error rate. All right, well, here we can look at an example table to follow up from our previous analyses. Note that we still have our 3 groups. We have our community service learning, group 1, our experiential learning, group 2, and our didactic learning, group 3. In this software, the report for the Tukey's HSD, and that's what I've asked for here, comes out as a difference between groups. So I have community service learning, didactic. It calculates the mean difference, the first minus the second, I minus j as it's labeled here. It calculates the significance of that, and that gives me a confidence interval of that. I'm using Tukey's HSD. Note that the Bonferroni, because it's more conservative, would have a higher statistical value, or excuse me, a higher significance value. These are the p-values, remember. The p-values would be higher. That's more conservative, more likely to be above alpha. And the confidence intervals would be a bit wider if I used a Bonferroni rather than an HSD. But because HSD is perfect for these pairwise comparisons, that's the one I'm using. Here, quickly, I can see that there is not a statistically significant difference between community service learning and experiential learning. Community service learning compared to didactic, there is a statistically significant difference. Experiential learning compared to community service learning, well, I already looked at this one, but in the opposite direction. So now this is doing experiential minus community service learning, which is a negative number. Community service learning minus experiential was positive. This means community service learning is bigger, which we saw in our graph. So smaller minus bigger is a negative, bigger minus smaller is a positive. In any case here, experiential community service learning, we see that same p-value as we saw earlier, not statistically significant. Experiential versus didactic, this indicates that there is a statistically significant difference between experiential and didactic. It's a little bit closer to the border, closer to alpha equals 0.05, but still below it, so still considered statistically significantly different, even with the Bonferroni corrected p-value. Again, we don't have to do that here. We are already correcting our p-value through the Tukey's HSD procedure. Last but not least, we have didactic compared to the first two. Again, we already have these numbers in the opposite direction in the previous results we've looked at, but we do see didactic is statistically significantly different than both. Now, I should mention here that I can break this down and write up all the text that I just mentioned, but what's often done when I'm summarizing this is that I often think about it a little bit more to try to come up with a little bit more of a concise summary. So for me, the concise summary that I would have here based on this post hoc analysis is that community service learning and experiential learning are both statistically significantly higher than didactic. So didactic is statistically significantly lower than both community service and experiential. But community service is a little bit better than experiential, but it's not statistically significantly different. And recall, when it's not different, I'm not going to then write in my statistical story, community service is a little better than experiential, because I don't have evidence for that. These inferential statistics say, do you have enough evidence to claim one is that their difference is different than zero? And the answer is no, I don't have enough evidence here. So community service learning, experiential learning, both seem like good options compared to didactic, but I don't have enough evidence to differentiate between them if one is more effective than the other. That would be my formal write-up in this particular case to interpret this type of post hoc analysis. All right, well, this has been our discussion on post hoc analyses. In the next lecture video in this lecture set, we will jump into some fancier types of ANOVA.